My name's Ty, and I've been working on various aspects of mobile developer platforms for the last 4 years. I started my journey into this little bit more niche space of Android when I was at Evernote in 2012. I continued it for a while when I was at Twitter working on the Fabric tools. And now I'm contributing to the developer platform at Uber, trying to build on our external API team tools for external partners to build on top of Uber and make businesses out of it. For those of you not too familiar with developer platforms, it's the arm of a company that focuses on the external API, the developer tooling and docs, SDKs, partner integrations, developer relations, and other sorts of outreach. Today I want to walk you through many of my experiences and war stories and just features I've built to help guide you in building your own platforms in the future, or just to have a better understanding of if you were going to try to build something against one of the existing platforms on mobile. So a traditional approach to a mobile integration against a web service may look something like this. You have a variety of apps on the device. Each one of those may have an SDK. That SDK is talking to an independent web service. And this approach has many benefits, such as more flexibility and the guarantee of the existence of the third-party code inside every app. But it has downsides as well. Every app bundles the same code, makes independent network requests, and caches duplicate data. I think a more interesting approach is to think about how to provide functionality that already exists in a first-party app to subsequent third-party devices that may be installed. And this could preserve some size and bandwidth for customers, as well as unlocking many interesting features and mixes of functionality. So I'll walk you through a few of these. Let's start with a recent project that I was working on. It was bringing a consistent deep link framework into the rewrite of the Uber Rider app. So for those of you not very familiar with deep links, it's a general term used on Android and iOS to represent a URI that an application can handle for a specific intent from the user. An application will initiate the URI here, and it starts the ride request flow in the Uber app. Now, the URI is just made of a series of parts that communicate the intention of the deep link. In this example, the scheme indicates that the Uber app can handle it, and the ride request is the action that we want to be providing. The query parameters here are the information for how the ride should, the parameters that are needed for the ride. In this case, pickup location, lat and long. By registering the URI information in our Android manifest, we're telling the Android system that our app can handle this URI, and that when the system throws it, to alert us and allow us an opportunity to handle it. This can be supplied in the data field of an intent that's incoming, or by the user clicking a URL somewhere that's been linkified, like a browser, email, or any other app. Here we're specifying the scheme and the authority in the intent filter, so only the URI that matches our exact requirements will start the request, or start the activity for this specific intention. But since deep links are general terms, and I mentioned that it's used across platforms, including web, it's more common to use a standard HTTP link that the application can handle. The same data is provided, but in a standard HTTP URI using the HTTPS format here. But what would happen when the application isn't installed on the device? How would that flow work? Should you just drop the user in Chrome? Well, because we're using a standard URL, the browser will handle opening this. But this is a great opportunity for you to provide the best possible user experience to get the user to install the app and then engage in the specific intention that they had. Now, you want to do this by taking the user to the browser, and you can safely make some assumptions at this point. If they've landed on here and their user agent indicates that they're on a mobile device, they probably don't have the app installed. So a standard way of approaching that is to fingerprint the device so that you have a unique identifier representing that, and then to forward the user on to either the App Store or the Play Store, depending on the platform, with that referrer information. Now, once the user is on the Play Store and they install the application, and they launch it for the first time, the Play Store will emit a broadcast that your app can register to receive called the installed vending broadcast. And inside that intent, it will have the referrer information that you originally passed in as the query parameter to the Play Store. Now, this allows you to take that out, run it through a URL de-encoder, and potentially have either a unique identifier, if that's the way you were encoding this, so that you could access your web server and say, hey, what was the deep link the user was originally trying to do before you forwarded? Or perhaps you're not caring about attribution or affiliation as much, and you just want to say, hey, I passed the full encoded URL deep link inside that query parameter. You can go ahead and parse that out and run that. But at this point, regardless of your approach to that, the app has the original deep link that the user clicked before the app was installed, and you can continue them in the flow. With Android Marshmallow 23 and up, the application can be set by default to handle a URL. And this prevents other applications like Chrome from trying to open a standard link. And it provides a much better user experience and an enhanced security model. To implement app linking, you just need to make 2 modifications to the existing deep link code that we showed. The first, on your manifest, you need to add an auto-verify tag to true. And this tells the system for anything that's declared here to automatically try to verify that you're the default handler for this. And how does it actually validate that? Well, the second part of this is that you would need to create an assetslinks.json file that exists on your domain. So if we were saying we could handle www.uber.com, we would need a assetslinks.json file existing on the host for uber.com. And the content of that would be your public key store fingerprint for the APK that's installed into the device. So the Android system will take that APK when it's trying to auto-verify. It'll grab out the public signature. It'll parse this down. It'll say, hey, these signatures match. And now Android will open that by default when a user engages with that. Now, while deep links can be very powerful, they can also spawn their own set of unique problems and bugs. And here's a really fun bug that I ran into while trying to deserialize a deep link. Does anyone care to take a wild guess at what they think is happening in this screenshot? What's that? I can't read it, sorry. Can you see it? I cannot, but the craziness with the lines should kind of give you an indicator of.
Oh, was it I thought it was a bridge. Data was probably manipulated when you tried to parse it. Oh, that's a map.
That's a map.
There's a bunch of routes being created.
There's millions of routes being created.
Okay. So the parsing was problematic.
Okay. Here, we'll dig in a little bit. So here you can see the deep link that caused this issue and the problematic code that caused it to happen. So the deep link, we have just a standard URI. We're specifying lat long, 23 dot whatever, 121 dot whatever. But there's a very subtle bug here. You'll notice I'm using locale.getDefault. Now, in some languages, in some locales, a comma is used instead of a decimal for indicating a percentage of a number. Now, if you'll notice, this is correct. It's a dot. And lat longs are represented internationally by dot. They are never represented by a comma. But in this picture, if you look really closely, and it might be hard to see, this is in Portuguese. So it was expecting a comma, saw the period, and the number formatter tried to be smart about it, didn't throw an exception, and actually just grabbed the last chunk of usable information off of each one of the strings. So in our case, we got a lat that was 3 million something, and a long that was 2 million something. So the fix for that was just to switch it to locale.us. Very simple. Now, unfortunately, this failed in many spots, because it failed here at the sanitizing of the input. Our routing logic also said, hey, if we got a lat long of 3 million by something by 2 million of something, somewhere in there it's doing a mod 360, and it's just creating route after route after route as that's wrapping around the world. Ended up with a very weird use case, as you folks can see. So another common mobile developer platform feature that we've built and that is used in general across all these platforms is to integrate authentication into the app to call certain endpoints. The Uber API has both privileged and non-privileged scopes for the different endpoints that need to be accessed. Non-privileged scope, for example, would be a little less impactful to a user's account. It may be something just to see past trips, where a privilege scope might be to initiate a ride request now, where someone is literally going to show up to pick you up. We would want to indicate a difference in those two scopes. Now, so when we are wanting privilege scopes to exist for these certain things, it takes a little more configuration for the user to set up a system that can reflect that. So there's this idea in general with OAuth called Threelegged auth that some of you may have heard of before. And it's the idea that the mobile client has a client ID, and that the consumer has also implemented a server, and that server has a client secret. Now, the client app will load the Uber login in a web view and hand it the client ID. And upon the user putting in their credentials, saying, I approve of the permissions that it's asking for, it returns an authorization code back to the app. Now, this authorization code is not an access token. It cannot make API requests yet. And so the client app has this code, and they hand it up to their own custom server that has the client secret. And now their custom server combines the secret and the code, and then hits an Uber API endpoint and exchanges that for a valid access token, and then hands that back down to the client. So as you could probably guess, this is a little bit of an overhead. You'd have to implement the server and the client and handle this flow through multiple systems. It can be a little off-putting, especially if you just want to stay in mobile land. Fortunately, it's an area that has been improved on quite a bit, and many of you have probably already used this improvement in many of your favorite apps. By integrating the authentication process against the first-party app on the device, as opposed to trying to do it through a web view where you have to log in, you can guarantee the integrity of the device, because that first-party app itself can act as that second factor, that server, with the additional guarantee of validity. Therefore, so in this more simplified process, a person that's implementing a consumer app of this would just need to start the flow with their client ID. The Uber app intercepts that through the deep links we talked about earlier. It then loads up the additional information that's needed, hits the Uber server, authorizes the user. The user also doesn't have to log in, so it's a better experience because the app is likely already logged in, and then can return a valid access token directly to the calling application, which is a much simpler process. So there's a few ways I've seen these built out before, and I've worked on these. I've built single sign-on at 3 companies now. The most straightforward approach is to have the third-party app call a URI that the provider app can handle. And that provider app calls a URI to redirect back that the consumer app is registered for upon completion. But another approach is to use custom actions and a bundle and an intent to initiate the flow with start activity for results, and then on the application, on the activity results, to parse out that information and try to get the key out of that. This is, unfortunately, a unique implementation to Android. So if you were trying to design a system that was for both iOS and Android, you would have already split out your 2 different implementations. This is, however, the way that the Twitter sign-in code was written. And that's primarily to account for legacy partners that already existed in the wild that needed to continue to work after a public launch of this. It's very important not to just randomly break APIs to appropriately deprecate things, but sometimes that that prevents you from making completely new API decisions when you would want it. A third approach that's similar to the second is to use the standard Android ordained way, which is to use the Android account manager to manage the flow. There's a bunch of built-in components in the Android framework that you would need to extend and implement, and we'll walk over those in a little bit. But that gives you the standard way of approaching this implementation on Android. Like the second one, it's only applicable to Android. And it does require additional permissions, which can break auto updates and be problematic for different apps. The Evernote SDK was built using the standard approach here, and I'll dive into the implementation a little bit later on. But like I said with that first one, with using the URIs, I think that is the most straightforward approach, and it works for both platforms. And there's actually an IEEE RFC out right now to standardize that as the way to do native sign-on in dealing between web and the apps on a device. However, it does have a some security concerns that need to be mitigated with other approaches like app linking or with setting the package explicitly, and then using custom queries against the package manager to check extra signatures to make sure it's the app that you're talking about, you're trying to talk to. So in a high-level approach, the client app starts a URI that if registered by the provider app, it can handle, and if not, then it follows the browser auth flow. So it goes to the standard OAuth on the browser. Not as good of an experience, of course, since with the first one, if the app is installed and signed in, the user doesn't have to put in their credentials twice. Once the user has granted approval on either one of these flows, which at this point is agnostic to the end user, we follow that redirect URI. And the consuming app has registered for that in their manifest, and so it will launch back into their application, and they're able to parse out the access token from the query parameters. But as you can imagine, when authenticating a user, security should be a really high concern. And firstly, I recommend that on both sides of this integration, this contract, that you set the package names to make sure that you're being very specific on the app that you're trying to talk to. If I had two apps installed on the device and both of them could handle the same URI, it might put the user in a confusing spot when they see the intent picker launch and they have to pick Uber or Chrome. They would say, what would I do with Chrome in this? But by setting the package explicitly, you're telling the intent user to kind of run with that package name. But in continuing to mitigate security flaws, you should also take care to validate the signature of your connecting app, that it matches what's expected from the public key. Similar to what I showed with the app linking earlier, where you had the public key on a server. In this case, if you have two different apps, it would be important for the app that's trying to connect to look at the package manager to look up that APK and say, hey, does the public signature of this thing match what I have encoded as the public key for that application? But does anyone notice any bugs or anything that's wrong with this specific code right away? If not, that's fine. I'll explain it. Let me give you a quick visual of the trust chain that a key store uses to sign your APK. You have the root certificate authority, which is provided by the device. And then you have a number of intermediate certificate authorities before finally signing in a chain your SSL certificate, which if you then look at your APK, all the signatures, you'll see a number of these. Now, if you look back here, when we say get signatures, this gets an array here, signatures. And so you have a number of signatures that are coming back from the APK. So what those signatures are is it's the public signature for every one of these guys. Now, it's pretty easy to generate a trust chain. It may not necessarily go up to root, but there is a known security vulnerability called the fake ID vulnerability, where you can write a quick little Python script that takes the public key of an app. You take that public key from the cert, and you generate a fake CA with that public key. Then you programmatically tell it to sign a generic SSL cert, a developer key, whatever. It doesn't really matter at this point, because now you have a trust chain that's of two. It doesn't go up to root, but one of them is signed using the public key of a real key store. Now, this is super problematic because in the previous code, we say, hey, if any of these contain the valid public key, continue, it's fine. And using this logic, I was able to generate a fake app that intercepted the auth requests for many different open SDKs today, everything from Facebook to Dropbox to Coinbase to Microsoft Azure, on older devices, on older versions of Android, where this is still a problem. This is no longer a problem in the wild, mostly because of Google Play Services updates, as well as PRs and bug bounties that me and a number of other people have sent against these SDKs to get these fixes resolved. However, here's the implementation for the code of how it should operate. Now, it's very subtly different than the previous code. Instead of checking if any signature matches, you say, if any signature does not match, because all of them will be signed by the same public key that signed the entire APK. And when you do this, if you have any outliers, if it doesn't go up to root, whatever, it doesn't matter, this will flag it. Now, this is probably only an issue right now on a small subset of devices under Ice Cream Sandwich and maybe some older Amazon Kindle devices that don't have Google Play services, but it wasn't too hard to reproduce in an emulator with some of those older devices. So I'm going to move on to another one of the integrations that we built out at Uber and how it kind of relates to some of the other stuff we're talking about. So we're working with Samsung. Samsung has this new personal assistant called Bixby that's a competitor to Siri and Google Voice. And they wanted to be able to book an Uber ride via your voice directly from it. And this required back and forth communication with the Uber service. They needed to start a ride and check the trip status and alert the user when the car is arriving and all the things you would expect. So we brainstormed a few different approaches here. The first one was just to use the web API. Just use, hit our API requests. And this would be great because it would allow for a range of use cases without any client-side changes in the Uber app at all. But unfortunately, it requires the user to OAuth with separate credentials. And it would, there's a very similar implementation on iOS that's standard with a ride-sharing intent that uses the standard keychain on the device. And so Samsung felt like this was a step down in the quality compared to iOS, and they didn't want to do this. We agreed the user experience wasn't that ideal. So next, we thought about using the Samsung app with the Uber app through deep links or IPC or a content provider to directly communicate back and forth between Bixby and the Uber app. And we'd create an API for each use case that it needed to fulfill. And while the user's already logged in, we'd be able to use their shared information. It would be very easy. But unfortunately, it would require additional maintenance on the app regularly because it would couple the features with specific APIs that we'd have to implement in the client, which would then probably reflect APIs on the server. And it can be a lot more complex when thinking about things like which version of the Uber app is this talking to, and what about deprecation or future changes? It would just require a lot of overhead from the team. So the solution we settled on was to use a mix of the two. We used an IPC, or an inter-process communication, which I'll get to shortly, with an internal service in the Uber app that communicates directly to our external API. It proxies it through. But as opposed to building one API to talk to per feature that was needed, we built a generic pipeline that the consumer can make a request through that would get signed with the key if they had a properly whitelisted client ID, and it would proxy it up to the external API and bring that result down. Now, this manages the authorization token for the user, and it allows the app to stay pretty stable since it's not really opinionated on the specific APIs. So how does IPC work exactly on Android? Well, first, you would define an Android interface definition language. This is like an interface, but it uses an AIDL extension, and then it auto-generates the code that's needed. And you must implement what's needed. You can then use this to communicate across apps or across processes. And it allows you to directly call members on it. So it can be quite powerful. But both the sender and the receiver must have the same concrete implementations of the classes, and the objects going across must be parcelable. So let's go over a sample implementation. Here we're going to create a lightweight AIDL class that can receive a GET request. First, we define the AIDL file with the methods we want to use. The type support includes primitives as well as the parcelable classes that I mentioned. Next, we implement the auto-generated stub for the AIDL file. And here we're going to validate the client ID as one that we want this elevated behavior to have. And if that's true, then we're just going to proxy this over to our actual service to make the request. If not, we're going to return an empty bundle, and they can handle the failure case. Next, we're going to create a service that, on binding, returns the API binder that we defined. Now, if you can only get one chance to return this, so if it's not ready and you return null, that's going to be cached, and that's going to be problematic if they try to bind again. So finally, we can consume that remote service in another app by setting up a service connection. It receives callbacks for connected and disconnected states, so we know when calls can be made on the service. We need to initiate binding and unbinding in the lifecycle methods of this component, fragment activity, whatever it might be. And what's funny about the onService disconnected is that it's only called when the remote service has an exception and quits. So you need to explicitly null it out in onPause. But once we have the service connected, in the onService connected, we can grab out the service that's handed to us in the callback. And from that point on, we can actually use that to directly communicate with the other process. So this wraps up this minimal look of how we built out a client-side proxy for Samsung's voice assistant that can be expanded to many other partners without client-side changes. And it even preps us for a future where we can integrate this directly with our SDK or APIs for all consumers to open up the platform. So this closes out some of the more recent work that I've been doing at Uber on the developer platform. But I want to move into something a bit older in my career when I was at Evernote. And it's a project that touched many different Android components that most developers normally cringe at using. So when I was at Evernote, we were tasked to work on a high-profile project, which was to directly integrate against Samsung's S Note. Now, you'll notice a theme here. Samsung likes to go to big companies and get them to make custom integrations because they have a large amount of market share. So that seems to work out well for them. There were a few high-level requirements to this project, though, that we had to meet. All the S Notes must be browsable in the main app among all of the other content of Evernote. And they must open directly from Evernote into the S Note app, and upon saving them, return back to the Evernote client so that the user felt like it was one consistent flow. And S Note needed to be able to asynchronously create and sync Evernote's content against its web service to make sure that there wasn't any data loss. So let's go over the more specific product requirements, how we broke this down, and then what it entailed for different implementations. So diving in a bit more, we needed this consistent contract that we could share for the integration. These were the technical requirements that we needed. We had to be able to get one or more notes for S Note. We needed to have an action that represented showing a UI list view that S Note could send a user to. We needed the ability to create a note from data provided or update an existing one. We needed the ability to delete notes based on the user's feedback. And we needed the ability to read the Evernote account information from the S Note app so that it could know if the user was logged in and how to appropriately manage that onboarding flow. Lastly, we needed to expose certain specific preferences, like the available space in the user's account, so that we could show the right user experience and not have any lost data. So we can take advantage of many of the standard Android components to meet the needs that I described. And so we'll go over a few more of these. The first that we'll need to do a bit of a deeper dive into is intents. And then we'll need to talk about using the content provider for when we need to work with more than one node at a time, which is what intents would be good for. We'll also need to talk a bit about the account manager, which I mentioned earlier in this talk around the authentication. I'll give you a bit of a deeper dive into this, and you'll see why it can be a little hairy. Finally, we'll look at the sync adapter for optimizing network connectivity. So intents are one of the first components that new Android developers learn about, and for good reason. They're crucial to the communication between most components in Android, activities, fragment services. The system's just built on these. And they have a bundle or a key value store that you can just throw data in and pass it around between components. So that's pretty nice for having a nice API for moving around your app. But they're not that efficient for larger payloads. I believe the current recommendation is either 512K or 1 megabyte for the maximum size. So I wouldn't recommend sending a serialized file through an intent. But we can use the setData method on an intent to give it a URI that we can then use the content provider to get at that specific larger set of data. And I'll give you an example of that. It's also inefficient for batch operations. If you needed to do multiple things, the broadcasting system runs on the main thread. If you were doing a lot of parsing and throwing a lot of these, you could cause an ANR. Now, one of our requirements for this partner integration was that we needed to be able to batch upload all of the S notes that have been created on the device if the user chose to set up that account sync at a much later stage in their user lifecycle. So this is a great example when we couldn't use the intent. And last thing that intents have that I find was really beneficial here was custom actions. Going further, we could create a consistent API around these actions to give developers more of a sense of consistency to the endpoints that they're hitting from an app to an app. So you can start with an intent by providing more functionality today by quickly implementing some of the standard Android intents, not even custom ones. They're commonly used for things like sharing, which you'll see in many apps, and it'll prompt the user with an intent picker. There's also the send action, which allows you to send data to be used in another app. There's the send multiple, which is very similar to send, except you can send multiple pieces of data. View is very, very similar to send, except it has different intentions. Send is around sharing a piece of data from one app to another. View is around saying, hey, I have a file of a specific MIME type that I don't know how to handle, and I want to give it to another app on the device that can handle that. So imagine if it was a PDF and you had a PDF viewer. This would be a good place to do view. And then edit, very similar to view. It's extremely powerful, and it's also the one that I find most interesting that we're going to dig into to kind of run through the rest of these examples. But it allows you to have another application edit a MIME type that you can't necessarily do, and then return the results back to you. So there's several things to note here as we start to build out how we would have an editing example with an intent. We need to create our intent, and we need to set the action to edit. We need to specify the MIME type to be able to be handled. And we need to specify the data URI, which is the URI that references the file to be edited. Once we've built out our intent, we call start activity for result, which will launch another application that can handle this. And upon success of that, we'll receive the result back. On the receiver side, we would put an intent filter in our manifest that defines the action that we want to handle, as well as the MIME type. And this will allow the app to be picked by the system for this file. We then need to read the incoming intents in this consuming app based on the action, because we could have a lot of different intents that this specific application can handle. If it matches the credentials that we want, if it's the same MIME type, then we're going to go ahead and we're going to try to edit the data out of this. Then we're going to set the result, and we're going to finish. On the sender side, we're notified in the onActivityResult method, and after verifying that it was a successful operation, we can move the user forward with an updated file and whatever user flow they have. So there's some definite caveats when editing a file, and it's primarily due to inconsistencies of how this is implemented across a range of applications on the device, both as the sender and the receiver. So first is I highly recommend that you don't send the original file to the recipient app when you want to edit. There are many edge cases around this. For example, the recipient application may make an unintended change to the file, or may make an intended change to the file, but the user hits back and cancels it. But they had been writing it on every operation to that URI that you handed them. So the user comes back to your application, you receive a canceled result, but that application had written directly to the URI that you gave it, which had write permissions. Now, that means that the file was changed even though the user hit back. Back is often associated with a cancel gesture. So that would probably be unexpected by the user and a poor experience. So what I recommend instead is copying the file before you send it over, sending over the copied URI, and then informing your consuming applications in any docs or whatever to return that back to you when it's done. Don't always rely on the set results either, or the onActivity result. I found that there was many applications that weren't calling set results, or if they were using a different URI, or they weren't using any URI. So you need to check the URI you're sending versus the URI you're getting back, or no URI. If they're not using set result at all, and the user comes back, it may be an onResume. And if you're getting it in onResume instead, but you've given them the URI, it's still possible that the user made edits in that other application. So I'd recommend either using a content observer or checking to see if the file was modified directly on these sort of situations. You'd come back from that other application. You would say, hey, we noticed the MD5 of this file is different. You could prompt the user, hey, this file was changed. Do you want to save it? Yes, it's one extra dialog the user may not want to see, but it's probably a much better case than if you overwrite a file that they didn't intend to. So we talked about some of the standard actions that multiple apps support. However, when we provided Evernote in this way, we need to think about providing the app itself as a platform. And that allows you to be much more specific as well. In addition to those we discussed for the Evernote app, we also created this rich set of intent APIs. We modeled it after the standard CRUD, so we provide a comfortable experience for developers to come in and kind of understand what was going on. For example, and we did this for many of the different model types, like notes, notebooks, users. For example, if the list intent is used here, we would show the UI element for the list. But if new was used, it would open the composer with the draft or potentially any information they had sent over that you wanted to prefill. Here's an example of how the caller would call to engage, how a caller could engage to start a new note with that intent API that we defined. All they need to do is set the custom action. In the intent, they could put in the information that we needed to parse out, and they set data with an image URI. When they call start activity for result, that's going to open Evernote with that intent that we defined and allow the user to continue with a flow that they would make sense to them. Now, although these sorts of techniques work great for single pieces of data, let's talk about how you would interact with larger sets of data. A content provider is just a well-defined contract to consume and write data for your app. And it's traditionally backed by SQLite. However, it's just an interface to be implemented, so you technically could back it by anything you wanted. And where intents are great for sending small chunks of data back and forth, the content provider is designed to query large chunks of data or work with individual files. And the implementer must define a unique authority for your content provider so it can be looked at by the system. That means that there can only be one unique. The provider has to be unique per entire system. So you could have a failed package install if you were trying to install another app that had the same content provider URI. I've actually seen this before in different SDKs that defined their own content provider using something generic, and multiple apps used that SDK, and it would cause an issue. So be cognizant of that. So let's start with some examples of the content provider and how it fits back into potentially our edit example. Like the URI I mentioned earlier for deep linking, the content provider also uses a URI for lookups. We have 4 main attributes: the scheme, authority, data, and ID. Most content providers use the scheme of content, although that's not required. The authority is that unique authority that I described a minute ago. Data often refers to a table. There would be a regex lookup inside of the different methods in the content provider on the path. And then in this case, ID would be an attribute that you need to additionally apply to the user's table for the lookup. So these last parts are very important when a database may have multiple tables. So let's look at an example of querying with a URI like that. Here we're providing the query method that's implemented on the content provider. You'd match the URI and set the table to the user's table when it matched. Now, if I need to append an ID, if that ID came in, then I would go ahead and do that here. And then we apply the remaining methods to the query builder and return a cursor for the consumer to use. Now, once we built the content provider in the providing application, we need to be able to access that data in the consuming application. So we'll hit that query method on the content by using a content resolver for the URI we talked about. Now, this implementation could be used by your own app or an external app, depending on the export flag and the permissions that you have set. Just like we can serve data from SQLite, we can also serve files. And that's crucial for our edit example. So we have the traditional methods on the content provider, like query and insert, to go along with our editing example. I'll show one here that makes a little more sense. We have OpenFile, which returns a parcel file descriptor. There's a similar method called OpenAssetFile, which is designed to open subsections of a file, which is great at getting it like a resource in your APK, since it's a zip. But for getting something that you may have pulled down as content, OpenFile will pull it off disk. Here we are assuming the URI path that was handed to us matches our scheme on disk, so we're going ahead and we're doing that lookup. If that wasn't the case for you, you would need to do your own logic to find the path. Now, the majority of this work is setting the appropriate file mode and handling creating the file if necessary before we pass it along to the consumer. So that provider serving files wouldn't be really useful if we couldn't get at it. So we can use the content resolver to go after this with OpenFileDescriptor. Now this returns back a parcel file descriptor, which has helper methods to get at a file descriptor, which then can be proxied to give you input and output streams that can be used the standard way you would want to use. Even Bitmap Factory, for example, has a method to read an image straight out of a file descriptor. So the account manager is the system component that groups accounts provided by implemented applications. This is the next part of what we're going to need to kind of discuss as we push forward getting to the sync adapter, which was the last one that I called out. The accounts can be accessible to other applications, both for discovery or for interaction. So this is a better user experience. And it provides helper methods to store account data, like tokens, as well as assistant tasks like refreshing the tokens. It also provides a level of consistency for the end user where they can view and manage the accounts that they have on their device. So it's a little better for user transparency. How do we track our own app's account here? Well, we need to extend two classes that Android provides. The first is the abstract account authenticator, which is a service that the account manager communicates with. The second is the account authenticator activity, which is an activity you'll create to handle the login or sign-up flow. Here is a diagram taken straight from the Android developer docs, which is not the most clear. You have to dig into individual pieces. But I'll try to walk you through a little bit of what it's doing. The process begins by trying to get an account token, and on success, a callback is called, which contains a key intent or it does not. And the key intent, if it is there, it contains information on how to start the authenticator activity to finish the process. Or if it doesn't, it'll contain the token information directly in the bundle to be parsed out and used. Now, on error conditions, those will be reported back with the error callback. So I'm going to now walk over a couple different pieces of the implementation of what you would need to define as the provider, and then how you would consume that as a consumer. So in the provider, you need to implement the addAccount method in the abstract account authenticator. And it's called when the user wants to add an account for your application. So if they were in settings, they clicked the overflow and hit addAccount. You'll want to return a bundle with the information on how to start your authenticator activity, which is the one I mentioned earlier you would need to implement your login or sign-up flow in. This is called directly by the account manager, and we proxy that through this bundle. And then we can set the activity here to the specific one. GetAuthToken is another method that needs to be implemented here by the provider. This is called by the account manager when requesting the token. So this would be a consumer application saying, hey, provider application, I need an auth token for you. So this goes back to the native sign-on that we talked about with a completely different implementation. Instead of using URIs, this is using the account manager and calling GetAuthToken directly. This is the meat of the implementation. First, we extract the username and password from the account manager. This is a terrible example. You would not want to hold on to a username and password in this. You'd probably want to hold on to a token, but this simplifies it. And then you'd ask the server for an appropriate auth token based on the current credentials. Then in our successful code, if we got an auth token from the server for the consumer app, we could return that to the calling app. But if we get here a little further down, then we couldn't access the user's password, so we need to reprompt them for their credentials. And we do that by creating an intent to display that authenticator activity again. So you can see this is the common activity that you're trying to take the user to whenever there's an authorization issue. But if we're adding a new account, each application will have its own custom authentication flow. But at the end, we need to handle a couple things for the account manager so that it's accessible to the other calling apps. First, we need to create the account based on the username and the account type. If we're adding a new account, then we have to explicitly add it to the account manager as well. We then set the auth token that was returned on the account manager itself, and then we can populate an intent with all those extras that are needed to be read by the account manager. And so we can call setAccountAuthenticator results. The account manager can then parse all that out, store it appropriately, and then a consumer app going forward can potentially get access to those. And it can continue the previous flow that we discussed. The sync adapter is it's a bit more notorious to get working, and it's one of the requirements that we needed for this project. And it requires both the content provider that we did the implementation of and the account manager that we did the implementation of to be there before you can implement a sync adapter. Often people create a stub adapter, or stub versions of those two, just to get the sync adapter working. At a high level, it's a great efficient way for the platform to control your syncing data on a regular schedule with the web service. And it also exposes the sync cycle to the user, so you have better data transparency. And since the system optimizes running this when the device already may be running and syncing other things, it's going to prevent wake locks. It's going to help with battery life. It's going to help keep the number of open WebSockets down. And it can be provided and accessed by third-party apps, which we needed for the Samsung integration because they needed to be able to kick off a sync with the Evernote web service after they handed us local data. Then they needed to be able to show their user UI that indicated it was synced so that it would give them confidence. And in addition to interval scheduling. It's great at working with Firebase messaging, Google Cloud messaging, to kick this off. So how would we go about implementing our sync adapter? Well, it's actually pretty simple after we got the other two big chunks out. We just need a subclass, the abstract threaded sync adapter. And the most important method here is the onPerform sync, which is called at the beginning of the process. It already runs on the background thread. So we don't need to worry about blocking. Now in this example, we use the account manager to get the account we stored earlier. And then we can request images from our server and finally store them using the provided content provider file, content provider client. We also need to create a service for the sync adapter to bind to that's actually doing the logic. And it runs in the same process as the main application. And this gives our sync adapter access to resources and account information that live with that process. After creating the Java classes, we need to create a metadata class that lives under res.xml that defines how this interacts with the content provider and the account manager. This is why you had to have both implemented. And we also define the account type that would be explicitly referenced in the get account. You can also have some other things like allowing parallel syncs if your code is smart enough to handle multiple accounts. To wrap it up, we just need to add the service to our Android manifest. And then be sure to include the metadata about the sync adapter that we just created. Now that we've got the sync working, how often should we do it? Well, assuming that we wanted to sync on a polling schedule, let's say every hour, which granted is quite ambitious, and I'd recommend you think about your own use cases and try to punt that out. We'd be tempted to implement something like this using the sync adapter. Now it requests that our sync adapter be kicked off every hour based on the unique content authority assigned to our service. However, assuming you have a grumpy ops guy, he may come back to you after you launch this and show you a graph kind of like this and say, why are you DDoSing our services? Which happened at Evernote. It turns out that most carriers fire down a network tickle on the hour every hour. And so at all these different services, we had millions and millions and millions of phones waking up, pinging our service to see if there are any changes in their account. So how would we fix that? Well, here's a slightly varied piece of code. It's very similar to the past slide, except that we randomly add up to 5 minutes on the sync schedule. It's called a jitter, and this creates a natural distribution over time. So it will be much more efficient for hitting our end services. So we've met the product requirements for all the integrations that we've talked about. They've been fulfilled. So let's cover those real quick to wrap up. Remember at the beginning of the project when we talked about the requirements for the S-Note project. Now we've covered all of those Android components that could fulfill those. Let's talk about how they solved our problem. For getting notes, we used both intents and the content provider, depending on the batch size that was needed. For listing notes, we used intents. For creating and updating, again, we were able to use both the intents and the content provider, depending on if it was a singular or a batch operation. For deleting notes, we could use the same two components. For account syncing, we were able to use the account manager and the sync adapter. And lastly, for getting specific preferences, like the account space, we can use the content provider to get at this. Although rewarding to build these systems out, debugging them can be really challenging. So I'll give you a couple quick tips before we end it today. In my experience, many of these integrations are device specific. You may be building against specific cameras on individual manufacturers or specific products. Setting debug points in one process and switching between them can be really problematic. So you need really good logging with this. It'll be your friend. I also recommend building mock integrations for how you expect this to be consumed that you can automate testing for as well. Unfortunately, not all these local APIs are the most discoverable, so you'll want to also communicate these very clearly to your developer audience, your consumers, through things like clear developer docs. You'll also want to have a good channel for getting user feedback to make sure that when there are problems, you discover them quickly. Even consider a beta channel. Lastly, rely on great tools to get this information from the wild, things like Crashlytics or Firebase, to get both crash reporting data and analytics on this so that you can measure your entire user base to make sure your integrations are working successfully. I hope you had some great takeaways from this today. I'm excited to see more apps in our ecosystem that integrate with each other. I think it's a really unique element of Android, and I'd love to see more of it. If you want to see more of the kind of stuff that the Uber developer group does, the integrations, check out developers.uber.com. If you'd like to work on this sort of thing, my team is hiring, and I'd love to get a chance to chat with you about it. So feel free to come find me or DM me or email me. I'd be happy to chat. And I may have a couple minutes for questions before we have to wrap up. If not, you can come find me after.
Questions?
How do you handle security for the integrations to make sure a malware app that poses as a game isn't just sucking up your Evernotes?
Absolutely. So when I was editing content today, I actually deleted the entire section of using custom permissions. That is definitely an area I would suggest taking a look into. You can define permission levels, permission groups, and custom permissions on most of these components. You can define those either programmatically or in your XML manifest. For most of these, we would define custom permissions that the calling app would have to implement in their manifest. Or if it was on later versions of Android, they'd have to prompt the user for runtime permission to access that.
Anybody else?
One there.
Sorry.
Well, you hinted at it when you said documentation and about your own contact points and contracts, but hypothetically, if I wanted to integrate with, like, say, a popular messaging app, how would I go about finding what interfaces they've implemented?
It depends. There's not a very good standard way to get at a lot of those right now. The best spot is going to be to find their developer docs, because if they have an open platform that they want you to integrate against, then that's a good way to get information. If you were instead to go a little more of a discoverable way, and say you open the apps, maybe you decompiled it and you looked at their manifest, or you programmatically looked at what things, what intents maybe they could be hidden. You might run into issues where if they haven't publicly documented those, they didn't intend for those to be used by public consumers, and they may break you in the future. Or they may send you a cease and desist. You may be using them and that's not intended. That's not going to happen with the standard Android intents, hopefully, but there's that potential if you were to go that other route. So developer docs is a great way.
Anybody else? Thanks, Zach.
Thank you.